All right, kids, hope you're doing well. We are moving on to section 11.2. And this opening proof, I would like you to pause this video here in a moment, and I would like you to go through it. I didn't even give you room to do the whole thing. You can just mark up the diagram and just kind of think your way through it. And as long as you're comfortable, then come back, start the video again. I am going to talk through it quickly here because it is important. It does lead us to a new theorem. Okay. All right, so remember this notation means that we're circle O, that's O is the center. We're given that OX is perpendicular to AB. We're given that OY is perpendicular to CD. We're also given that OX is congruent to OY. That means that these two chords, AB and CD, are both equidistant to the center of the circle because these segments are congruent. We have to prove that these chords are congruent. I'm hoping that when you thought through this on your own, one of the first things you thought of was drawing in radii. These radii are, of course, congruent, and it leads to congruent triangles by RHL. And of course, if those triangles are congruent, that means this segment and that segment are congruent by CP/CTC. Now, there's a couple of ways for us to finish this up. One is to do the same thing up top here. Make these triangles up here, get these two triangles congruent by RHL just like we did, get these two segments congruent, and then finish with addition. That works just fine. Another way is to use what we learned in section 11.1. Remember, if a radius is perpendicular to a chord, that's what we're essentially given here, because we could extend OX and make it a radius if we wanted to. If a radius is perpendicular to a chord, it bisects the chord. So we have bisection happening here. We have bisection happening here. So if this segment is congruent to this segment, this whole thing has to be congruent to that whole thing by multiplication. Okay, so what does this give us? This gives us a new theorem. So remember, we were given that OX is congruent to OY, okay? And you can always, once you have that, I mean, we just proved if chords are equidistant to a circle's center, then the chords are congruent. Okay? The converse is also true. I'm not going to prove that one though. But if chords are congruent, then equidistant to the circle center. And we're not going to do a lot with proofs, especially this particular quarter with the goofiness, with the remote learning. But we're certainly going to be applying these ideas in problems. Okay. So two theorems for now. There's also going to be some more new stuff today. All right. So moving down to this next one, I already put the given information on the diagram here in black. And what we're going to be talking about is a couple different things. First, we'll talk about something called a central angle. All right. A central angle is made up of two radii. So this angle down here, we got concentric circles. That means they have the same center. This angle here is called a central angle. And this 60-degree angle is a central angle for this little circle, two radii, and they're the angle in between. It's also a central angle for this big circle, two radii, and the angle in between. Okay? Now, I hope you realize, I mean, all you guys know that there's 360 degrees in a circle. So a central angle, it doesn't matter how big that circle is, it's always 360. Okay? The central angle here will have the same measure the degree measure of its corresponding arc. So this word measure here, it's talking about the measure of arc AC. When it says measure, it's talking about the degrees of the arc. The measure of this arc AC is just going to be 60 degrees. All right? Because a central angle is always equal to the arc that it intercepts. But the interesting thing is this central angle is also a central angle of this big circle. So the measure of arc BD is also 60 degrees. You know, it's 360 if you go around really small, it's 360 no matter how big the circle is going around. Okay, so the degrees of a central angle equal whatever arc is intercepted by those radii. Okay? Now, notice how questions C and D are also relating to the same arcs that we did in A and B, but there's no little m in front. Here, we're talking about the length, okay, the length. The length is different than the measure. Measure is degrees, length is the actual distance. Whoops, sorry about that. And clearly this arc here, BD, is longer than arc AC, okay? And this is why, you know, when you're a kid and you go to the merry-go-round, you take the horse all the way to the outside because it's a little bit more fun because you're going faster. You're covering more distance per revolution than the kid in here is not going as fast because it's spinning at the same rate. All right, but they're covering more distance the further out you are. So to find the length of an arc, it's simple. It's just a fraction of the circumference. You guys all know that circumference is 2 pi r. R is 5 for the little circle. But that would give you the whole circumference. We just want this arc, and that would be 60 over 360, which of course is 1/6. And then I'd multiply across, and I would get 10 pi over 6. And that would, of course, be reduced to 5 pi over 3. All right? That's the actual length. So the measure is 60 degrees. The length is 5 pi over 3. Now, your default is always going to be to give answers in simplified radical form or in terms of pi. Only go to decimals in 3.14 if you're specifically told to, or if the problem set asks you to approximate, you know, something along those lines. This is our default, it's an exact answer. BD is going to be the same thing. 2 pi r here, of course, is 10. It's still times 1/6, and you end up getting 10 pi over 3. Arc BFD, remember, we talked about this the other day. That just means you're talking about the major arc. That's why the F is there. So you want to go around through point F. Clearly, if this is 60, that's 60. And arc BFD would have to be 300. All right, so we talked about this the other day as well. Minor arc. Minor arc is the short way around. That is your default. You should always be going the short way around unless you're specifically told otherwise. Major arc, so you're only finding the major arc if you're specifically told major arc, or if you have this kind of notation like an E above. That's the long way around, and that's only if specified. Semicircle, of course, is 180 degrees. You guys know that. Okay, I've sketched another circle out here. If you need to pause and sketch this, there's another angle that we need to talk about. Okay. This angle right here, that's the angle I'm talking about. That's called an inscribed angle. All right. The inscribed angle, this red angle, you see how so an inscribed angle is made up of two chords. Here you have chords AB and chords BC. The inscribed angle intercepts or creates this arc way out here. The inscribed angle is always half of the intercepted arc. Okay? So if this was, 100 arc AC, this angle would be 50 degrees. Now, I'll do a super quick little proof. There's three cases you'd have to look at. I will only look at one. What we would do to prove why this angle is half of that. So what we would do is we would draw in these two radii. Okay. Now remember, we just created a central angle here. So this central angle has to equal the measure of this arc. We're going to draw a diameter through the center. Okay. Now, remember, we just created an isosceles triangle here. This is congruent to that because it's a radius. That means these angles are congruent. We created an isosceles triangle here as well. That means these angles are congruent. All right, now this is the cool part. So remember, this angle here, that would equal the measure from here to there. Remember, this is an exterior angle to this triangle. So this angle has to equal the sum of the remote interiors, okay? That means, if this is equal to the sum, okay, that means that this angle here is half of this, which means this angle is half of that. And you do the same thing down below. Exterior angle equals this sum. So this angle here has to be half of this. And that means, and then this, of course, is equal to that. So this whole angle here has to be half of that arc. That's an ascribed angle. We'll talk more about ascribed angles later on, but you need a little bit of that right now. Now, if you go to the back side or the next page, there's a big problem here. And I put all the given information on the diagram already in black, but there's some additional information I need to give you. Okay. I'm going to do that down on the bottom here. And I hope that this makes sense. So whenever I create a drawing, let's say that these two central angles are congruent, okay? If those two central angles are congruent, that of course means that these arcs have to be congruent. And the converse works as well. If you are given that you have congruent arcs, then their corresponding central angles would have to be congruent. But there's other parts that we have to consider as well. We could also, this central angle, if we connected those two parts, we create a chord. Let me do that in a different color. So we have that chord and we have that chord. But if you have congruent arcs, then the corresponding chords are congruent. So we have a bunch of things here. If congruent arcs, then corresponding chords congruent. If congruent arcs, then corresponding central angles congruent. Okay. Now, if you have, okay, this will come back in a moment. If you have congruent chords, then the corresponding central angles are congruent as well. And the converses of all these are true too. So this is referenced in your textbook in section 11.2. It's on page 822. You might want to take a look at that. But so you have a bunch of tools here. Corresponding chords congruent gives you angles, gives you arcs, and vice versa. So all plus all the converses. So there's 6 things here altogether. Okay, you might want to pause this for a second and then just kind of try this problem up here and come back here and I'll talk through some of these problems here in a moment. Okay. All right. So hopefully you try this yourself. I'm just gonna kind of show you what I'm doing here at first. I'm just gonna fill in some information before I even start answering questions. Okay. Now, if that's 100 degrees, let me change this back to red. That's this is a central angle down here. So that would be 100 as well. And I have this 40 degrees over here. So I'm going to go ahead and draw in this radius. That's helpful because remember, when you draw in radii, you create these isosceles triangles. There's an isosceles triangle that we just created. There was one down here. There's a skinny isosceles triangles in here too, because remember, that's the radius, and so is that. Okay. So drawing in radii is helpful. It leads to isosceles triangles. Just keep that in mind. Now, by drawing this one in, I created this central angle. That is now 40 degrees. Okay. So I'm just, again, working with the information that I got, trying to do as much as I can here in the middle, see where it all goes. Now, remember, we were given that this arc here, that's where the 2 tick marks are, is congruent to this arc down there. So that means their corresponding central angles are congruent. So I can find that out pretty easily by taking this 140, subtracting from 360. So if I take away 140 from 360, get 220, but these have to be congruent. So each of these central angles must be 110. I'm going to be able to do a lot just with that now. Okay. I'm going to be able to do a lot with that. I'm going to fill in some, remember this triangle here is isosceles. So that's 110. These are both 35. Look at this skinny triangle here. It's isosceles as well with a vertex angle of 150. That means these sliver angles are both 15. Okay. Here, let's see what else we can do. Here, look at this isosceles triangle up top. Vertex angle is 110, so all the base angles both have to be 35. So that's 35. This would have to be 35. If that's 15, that's 20. Notice how this 20, that's an inscribed angle here. And you see it's half of 40. So we could have gotten it that way as well. All right. So we just answered the first question. BAD is 20. There's 2 ways of doing that. The value of X. Well, let's see here. What are we going to do with the value of X? Remember, this is the measure. We could do That's the central angle. 110 equals 2/3 x plus 5, and you can solve that, and you will get x equals 157.5. Okay. What's the next one? The next one is ED. Well, remember, if this arc here is congruent to that arc up here, then its corresponding chord, the corresponding chords have to be congruent. So if this is 8, this must be 8 as well. Okay, we're almost there. Angle E, sometimes it takes a while just to find this stuff. So the next thing is saying the measure of arc EAB. Well, that's just going to be 210, right? Because you got 100 there, and you know this is 110. So that's 210. Angle FED. Oh, F was in the middle. That's right. So FED, we already found that. It's 35 degrees. Next one is measure of angle ACD. Let me see if I can find what happened to point C. Oh, that's way out there. So we got a big triangle here. This big triangle. All right. Now, if this angle is 20, remember this whole angle here is what? That's 50. So this angle has to be 130. So if that's 20 and that's 130, that's got to be 30. Okay. All right, got a couple more things to do. The length of arc EDB. Let's see, EDB. Well, I don't know if I'm going to, that's central angle of 150. So that would be 150 over 360 times 2 pi times r. You should be able to figure that out to 25 pi over 6. You should be able to do that without a calculator. And then the area, so sector, we talked about sector briefly on the previous lesson. Sector AFE, again, F was in the middle. So we're talking about this sector here. Remember, that's going to be the percentage, the fraction of the area, right? So that would be 100 over 360 times pi times r squared. Should come out to 125 pi over 18. All right. I hope that helps a lot. We'll call it